Hello. In this video, we'll continue to consider some summary measures we can use when exploring a data set. This time, we'll go to the data provided by our anthropologist. Here, we're trying to estimate age at death from skeletal remains, and in this video, we'll in particular consider the method of Ganji et al. We're interested in how well this method works, so we'll consider the difference between the estimated age based on the skeleton and the actual age at death for the 400 skeletons in our data set. We'll begin with a look at a box plot of these data. Although there are some positive values, we can see that most of the observations are negative. In fact, because the third quartile is negative, we know that more than 3/4 or 75% of the data are negative. So the method of Ganji tends to underestimate the age of death. It's also possible with this method to be way off from the actual age. Note that the minimum value is -60, meaning for one of the observations the estimate was 60 years younger than the actual age. We may want to investigate how unusual this value of -60 is. A modified box plot is one way to do this. Modified box plots were designed to detect unusual observations. To draw one, we first calculate the interquartile range, or IQR. This is the difference between the third and first quartile. For these data, the third quartile is -5 and the first quartile is -23. The difference is 18, so the interquartile range is 18. We then locate the inner fences, which are designed to contain most of the data. The inner fences are the values that are 1.5 times the IQR beyond the first and third quartile. For the lower inner fence, then, we calculate the first quartile, -23, minus 1.5 times the interquartile range, 18, which gives us -50. Similarly, for the upper inner fence, we calculate -5 plus 1.5 times 18 and get 22. In a modified box plot, the whiskers extend to the observations that are closest to the fences but still within them. Values outside the fences are indicated individually and are worthy of some attention, particularly isolated values that are far outside the fences. We can see that our minimum value of -60 is outside the inner fences, but there are also other observations beyond the fences, so perhaps an underestimate of 60 years is part of the range of values that might be observed with the Ganji method. Here's a quick summary of how to construct a modified box plot. It can help us both summarize the data and detect some possibly unusual observations. Here's the 5-number summary again for our data. The median is a measure of the center of the data. Another common statistic used to capture the center of the data is the mean or average. We'll introduce a bit of mathematical notation here. The Greek letter capital sigma is used in mathematics for a sum. The mean is the sum of the data values divided by the number of data points. Suppose we have n data points. For our example, n is 400, the number of skeletons. Let's represent our data values as x subscript 1, x subscript 2 through x subscript n. The subscript is an index for the position of the data value in the data set, and n is the number of data values. The mean is given the symbol x with a bar over it, and the formula for the mean is the sum, sigma, of the x's from the first observation to the last, divided by the number of data values, n. For the differences between the estimated and actual ages for our 400 skeletons, n was 400, the median, as we saw, is -13, and the mean for these data is -14.2. Notice that the mean is more negative than the median for these data. This happens because the mean is pulled down by the unusually large negative observations we observed here. We say that the mean is not a robust statistic. That is, it is not resistant to extreme observations. In contrast, the median is a robust statistic. Changing the values of the extreme observations does not change the value of the middle observation. Suppose we wanted to limit the influence of the extreme observations on the calculation of the mean. One option is to use a trimmed mean. To find a 10% trim mean, delete the largest 10% and the smallest 10% of the data, and then take the average of the remaining observations. For these data, we remove the 40 largest and smallest data values, and the 10% trim mean is negative 13.8. Note that the trim mean is closer to the median than the mean, as the trim mean is more robust to extreme observations than the mean. As an illustration of the robustness of the median and trimmed mean versus the mean, let's look at a smaller data set. Here are the salaries in US dollars announced in May 2012 for the 25 players on the New York Red Bulls, a soccer team in the MLS. I've put them in order from smallest to largest. As is typical in the MLS, a few players have very large salaries, while most of the players have salaries more in line with the average American. In particular, the salaries of Rafael Marquez and Thierry Henry, who had the largest salary in the MLS, are much larger than the salaries of their teammates. You can see just how unusual Marquez and Henry are by looking at a modified box plot. The box needed to be very compressed to fit them on the screen. Let's do some calculations. Since there are 25 salaries, the median is the 13th value in the ordered salaries, which is about $112,000. For the mean, we sum the salaries and divide by 25 to get approximately $518,000. We can see that the mean is much larger than the median because it is influenced by the large salaries of Marquez and Henry. If we want to remove their influence, we can use a trimmed mean. 8% of 25 is 2, so an 8% trimmed mean would remove Marquez and Henry, as well as two players earning $33,750. The trimmed mean is the average of the 21 remaining salaries and is about $128,000, which is a value that is much more representative of the salaries of the rest of the team. Here's a summary of the measures of center or location that we've discussed. The median and the trimmed mean are robust against extreme observations, while the mean is not.